This video is a tutorial about reconfigurable intelligent surfaces, which is a new component of wireless communication systems. In particular, we will have a look at this technology through the lens of array signal processing theory. And I'm Emil Björnsson. I'm working at KTH Royal Institute of Technology in Stockholm, and this is a joint work together with a number of students and colleagues over the last 5 years. So wireless infrastructure is something that we have had for many generations now, but it has also been improving little by little. So traditionally, in the 1G to 4G era, we used this kind of sector antennas that are focusing signals into a 120-degree sector down to Earth where people are, and fortunate users who are standing in front of them get a much stronger signal than if they would be radiating the signal from the base station in all directions. So we really are purposely sending the signals towards where users are supposed to be. But unfortunately, when we do that, we take away energy from other directions, and sometimes we want the signals to go there as well. So for example, here we have a blocking object, maybe a building, and there is an unfortunate user behind it that is not reached very well through this directivity of the base station. Possibly the signal could hit another building here and be sort of scattered around in this area here, but you see typical reflection properties of the building might still make the signal not face towards the user. So some users will be unfortunate in this kind of scenario. When it comes to 5G, we have been improving the technology at the base stations a lot. So now, instead of having one fixed 120-degree sector that we are sending the signals into and letting users take turns, all of a sudden many users can get signals at the same time at the same frequency, and we separate them through what we call multi-user beamforming. So we can send signals in different directions at the same time or frequency, and they can then contain different data. And here we see a number of fortunate users that all of them will get a good signal quality. We can still now, when we want to serve the user around the corner, beamform a signal directly towards this building here, but we can't change how the building is reflecting the signal. So even if we might get a little bit more power towards this unfortunate user, we will still have a reflection that we can't control. And this is what people are imagining in 6G, that we can deploy new infrastructure components that can control the wave propagation between the transmitter and the receiver, and maybe reflect the signal directly towards the user here and turn it into a fortunate user as well. So the idea might, for example, be here I'm standing in my virtual office, there is a base station sending a signal, and the signal would have to go through the wall, and when it does that, you lose 20 dB, which means that 1% of the power that hits the wall actually goes through it. So that is a large loss in power. In this scenario, the signal might go through the window and hit this area over here, but probably it will be reflected towards the far end of the room due to the geometry of wave propagation. So what can we do about that? Well, we could potentially deploy what we call a reconfigurable intelligent surface and create what is known as a virtual line of sight path. So the base station and me as a user are not seeing each other. There is no clear line of sight path between us, but both of us can see this surface here, and therefore we have a path that is reflected and virtually behaves like a line of sight path, if we can do this as is illustrated here. The name Reconfigurable Intelligent Surface comes from the following idea. It's a surface in the sense of it's a two-dimensional area that we are using in order to reflect the signal, and it contains a number of elements that have properties that we can change. And it is reconfigurable because these properties is something that can be changed over time, and is intelligent because we have the programming unit that can control these things in real time. So it might sound a bit like science fiction that we can somehow change the wave propagation in real time, but this is actually something that has already been demonstrating. So here is some work that we did a few years ago. So there is a base station here, a transmitter with a horn antenna sending a signal. Here is a copper plate and here is a receive antenna. There's 50 meters apart here, and the transmitter is sending the signal towards the copper plate, and it will essentially reflect it back because of the sort of incident angle being almost perpendicular to the surface. We operate here at the 5.8 GHz band, so that is a Wi-Fi band, use 20 MHz of spectrum and 13 dBm of power. Here you can see the received power in different blocks of 10 MHz, and it's these two 10 MHz blocks in the middle that is where we are transmitting our signal. And we can see that there is some noise outside the band, and then there is some signal power here, but it's very close to the noise floor. So with this copper plate here, we are not able to reflect much of the signal into this receiving antenna. However, if we change the copper plate to a reconfigurable intelligent surface that we have designed, the received signal power increased with 27 dB, meaning 500 times compared to the copper plate. So it's apparently possible to create this virtual line of sight path using a reconfigurable intelligent surface. And this was the first experiment of this kind in a real propagation environment that was actually documented in the scientific literature, which is why we are now receiving the ComSoc Stephen O. Rice Prize for this paper. The experiment in our paper raised the technology readiness level to a 4 or 5, but we are still far from having a commercially viable solution. In a paper a few years ago, we talked about RIS and 3 myths and 2 critical questions. There is another video here on YouTube about the myths, so I will just briefly mention them. Some of the myths that were spread in the early days of this technology was that relays, the traditional technology of relays, is something entirely different, which is not. Or that RIS would be much more efficient than antenna arrays, which is also a misconception, and that we will have similar path losses as mirrors. Even if we are creating these kind of virtual line of sight paths, it's very different from when you look yourself in a mirror. But more importantly, we were posing 2 critical questions in this paper that needs to be addressed before this technology can be really ready to be used in practice. And the first one was just, what is a convincing use case? It is nice that we can use it for particular things, but what will make it so important that a telecom operator or a building owner or someone else would like to actually deploy this technology in practice? And the second thing was, can we control this RIS in real time, in real systems? And the focus of this video will be on the second question, to find the answer to that one. But first I will say something about the first point. So there are many possible use cases that people have been talking about. The first thing is to let the RIS act a bit like a relay. So I'm standing here in a hotel room, I'm looking out over a city, and suppose I don't see the base station, but I can see parts of buildings that the base station can also see. Well, then I can deploy the RIS at a number of different buildings so we can create this kind of virtual line of sight path and relay signals around different kind of blockages or shadowing phenomena. Another thing might be that you have a multi-antenna array here at the transmitter and multiple antennas at the receiver and some additional objects around. But if these objects are just spreading out the signals, they will not provide us with any strong paths that we can use for extra communications. So the only way of communicating would be to send a strong signal towards the receiver and let the receiver focus a beam in the receiving mode towards the transmitter. But if we deploy reconfigurable intelligent surfaces on these other objects that were there already, we can shape how they reflect the signal so they all of a sudden improves the channel rank here, enables us to send multiple new beams towards this object and get strong virtual line of sight paths towards the receiver. So in this example, you might have 3 strong propagation paths instead of 1, which means that you can get 3 times higher data rates. Another option would be to improve localization and sensing. So a base station could send out signals that is bouncing an object and then receive them themselves in order to sense if there are objects at certain places or how these objects are moving and other kind of properties that they might have. And the problem is that from one base station's perspective, you have a rather limited view. But if you can deploy these surfaces and change how they are reflecting the signals, you can see objects from multiple angles, and in this way also be able to localize or sense objects in much better ways. There are many other options. One can use it for physical layer security, so you make sure that the signals are confined in places where the desired users are, and they are not reflected to any large extent to places where eavesdroppers might be, and in that way you can protect your systems from eavesdropping. Or you can use the surface to support wireless power transfer, which is happening when you have a transmitter sending out the signal. The RIS reflect the signals in a controlled manner towards certain IoT devices that might like to harvest energy to charge the batteries. And in that way you're recycling signals that were already there in the air and improve the wireless power transfer. And there are many other use cases here. Maybe relaying is the most primary one that we will see being used in the start of this technology. So if we have a closer look on that one, relaying around blockages, what is it that we actually are doing? We have a user device or a base station sending a signal. In this case it's the user. And we deploy this RIS to reflect the signal towards the base station. And we divide the surface into many small elements. In this case we denote it with n elements. And these have reconfigurable properties. Each element is controlled by some kind of varactor diode or some other device that is connected to a controller unit. This is where the intelligence is. And what you can change is the color here, which represents the impedance or phase shift that is assigned to the signal before transmission. We have a closer look at that later on. But the main idea here is that you would like to create this virtual line of sight path between the user and the base station, and you would like to do it in a more cost or energy efficient way than with some competing technologies, such as deploying more base stations or deploying a traditional relay. So that is sort of the hope. But it turns out that you need many elements here which have reconfigurable properties. And that is because we are not amplifying signals. We're picking up existing signals and we redirect them. And for that reason, we also need to know the channels when it comes to all of these different elements. And that is something we need to estimate using limited resources. And this is one of the main issues, the dimensionalities, that we will address in this video. And we will particularly do that by taking a look at the technology through the array signal processing tools and see how that is very handy in order to overcome some of these dimensionality issues. With array signal processing, we are usually studying antenna arrays and how beamforming works. So let me show you how that works in general. We have two transmitters here sending out signals at the same time and frequency. And we can see that these signals are propagating outwards and they will start interfere or superimpose with each other over there. And in particular, if you see here the wavefront seems to be crossing in this direction and be aligned upwards, this is where we get constructive superposition. So if I would start measuring the signal's strength in different angular directions, even if each antenna doesn't have any preferred directivity from the beginning, they just radiate in signals equally in all directions, well, if I measure the signal power, I will see that it looks like I'm sending much more power upwards than to the sides because of superposition. It's constructive upwards and destructive towards the side. If I now want to change in which direction this constructive superposition happens, well then I can delay or phase shift the signals. So in this case here, I'm sending out the signal from the right antenna a little bit later, and you can see that the wavefronts are then aligning more up towards the right here. That is where we're going to get constructive superposition. So if I have two antennas that has no preferred directivity from the beginning, and I transmit in this way and I measure the signal strength in different direction, it would look like I have directivity upwards to the right here and less towards the side, and you can get some side lobes as well. So the way that this is achieved is by sending the same signal but with different delays or phase shifts. That is what creates the directivity. And this can be studied using array signal processing. Particularly, there is something called the array response vector. So say that the signal arrives towards three antennas here, and there is a particular angle of arrival, phi. The distance between the antennas is denoted as delta. You can see that the wavefront first hits the leftmost antenna, then the one in the middle, and then the rightmost antenna. And the wave needs to propagate an extra distance to delta sine of this angle in order to reach the last antenna. This is some basic trigonometry. This turns into phase shifts. And we can capture them like this. We have no particular phase shift for the first antenna, we use it as a reference. Then for the second one, we need to move delta times sine of the angle. We divide that with the wavelength and multiply with minus j2 pi, and that is giving us the phase shift that the signal at the second antenna will have compared to the first one. And then for the third one, we had the same expression, but we have the extra 2 here because we have a 2 times delta distance between the two antennas, the reference antenna and the rightmost antenna. This array here is called the array response vector. So it shows you the phase shift at the different antennas. If this would be a receiving antenna array, what you would like to do now is to compensate for this phase shift. So you take each of the signal and multiply them with the same values as here, but with the plus sign instead of the minus sign. So 1 here plus j2 pi and the same phase shift value here, and then plus and the same value over here. And when you add them up, you will get the signal that is 3 times stronger in amplitude than you had before, because you add up 3 different signals in phase. What will now happen if I have 3 antennas and I'm sending a signal with the phase shift that comes from this array response vector? So 1, and then I had the minus sign here and the minus sign here, and you see there is a delta and 2 delta over here. For the same reason that if the signal comes in with minus phase shift, we compensate with plus phase shifts. Well, if you send them with minus phase shift, we will have plus phase shift over there. So the signal will not go towards the phi angle, but minus the phi angle. So the signal goes upwards here towards the right. So if we view each antenna here as something that first just receives the signal and then transmit it again immediately with the phase shift that you had over there, the signal will go up towards the right. And this is actually how reflection works. And one can interpret this using something that's also known as the Huygens-Fresnel principle. So suppose a plane wave comes in from the right here, then it hits the surface, first this point and this point and this point. Then we can apply this principle, which says that you can take the surface and divide into many small points, view each of them as a small antenna that picks up the signal, and then immediately scatters signals, send it out as an isotropic scatter. And this is what I'm illustrating here. The first antenna have sent out the signal, so it propagates further, then the second one, then the third one. And we can see how the wavefronts are adding up downwards here. So we will have a plane wave going out downwards. The incident angle is one number, and we have the same angle downwards here, but on the other side, so with the minus sign. So this is really what I was showing you on the last slide. So this is how a big, infinite-sized homogeneous surface would reflect. So a really big mirror would behave in this way. If we have a plane wave arriving on a finite size, but still homogeneous surface, so the length of this is W, well then the signal will go downwards, and we can measure the way that the signal is propagating out from the surface by considering the superposition of all of the small objects inside of the surface. But the signal will go downwards not as a plane wave, but it will spread out. It will have a beam shape, similar to what you would get if you had a W-length uniform linear array here. So the half-power beamwidth can be measured, and the typical formula is 0.9 times lambda divided by W. So the larger the surface is, the interval here in terms of radians, so angle, that we have a strong signal, will become smaller and smaller the larger W is. And when W goes towards infinity, we get this result here that is only going in one direction as a plane wave. But in general, a surface will reflect the signal and spread it out. This is the phenomena that we want to utilize. We want to have small elements that reflect the signals, and then we want to change the phase shift in order to control them. But if we are building a surface of a particular size, how big or small should the element be? Well, if a signal comes in from a particular angle, we know that it will leave with minus that angle, but it will also spread out around that one. And let us now have a look at what happens depending on how big the surface is. So this one is A times B sized. If the surface is 10 lambda, so 10 wavelengths in each of the different dimensions, the red curve here is showing you what will be the strength in decibels that you will get in different directions. So the signal comes in from pi over 6 and it leaves in minus pi over 6. And there is most of the power in that direction, but there's also some fluctuations here, even if there are 1/10 of the B's smaller. But the signal is really going in the direction that was determined by where the signal arrives from. If you make the surface smaller, so lambda by lambda, we get this blue shape, and we see that there is not much power going back towards the direction that the signal arrived from, but it spreads out in the other plane quite a lot. And if you make the surface even smaller, so 1/5 of the wavelength times 1/5 of the wavelength, well, you get this black curve here, which is almost circular, which tells us that the signal is coming from one angle and then just spreads out in all angles. So a large element behaves roughly like the Snell's law, saying signal comes in from one direction, leaves it minus that direction, while a small element is almost like an isotropic scatter. And it is the small element behavior we want to have. We want to have many small elements, each of them just spitting out the signals in all directions. And then we want to change properties in our surface in order to control where is this signal going using constructive and destructive superposition. So many small elements is best for controllability. This is a principle that we utilized when we designed the Reconfigurable intelligent surface prototype that I was showing you an experiment of before. So we had 1,100 elements in terms of 20 rows and 55 columns. And each of these elements is a patch which has some 2 varietor diodes that we can control. There are some dielectric substrate, and you find the details in this paper. But the important thing is that there is something called a reflection coefficient, which is determined by the difference between the impedance in the surrounding air, set 0, and the impedance that this circuit has. And depending on the differences here, we get a different phase shift and amplitude shift when the signal is reflected. Here are the results for this particular prototype. Let's look at the phase response first. So we have for different frequencies, we get different curves here depending on the bias voltage between these 2 different varietor diodes. If there are 0, well then in our 20 MHz band here around 5.8 GHz, we get a particular phase shift of minus, say, 120 degrees. Then as we increase the bias voltage, we get a phase shift that is increasing as well, all the way up here towards plus 120 degrees. So within our band, we can change the phase shift a lot. There are also some other phase shift that would happen outside the band, but this is what we care about in our communication scenario. Depending on what bias voltage we're having, we also get different amplitude responses. But you can see that they are between maybe 0.75 and up towards 0.95 or something like this. So they are practically the same, particularly when you're thinking about wireless communication where path losses might be 100 decibels, 1 dB back and forth is not much to talk about. So that's why we will focus on these phase shifts and how we can utilize these ones to change our communications. So they're roughly constant within this band here for the amplitude, and we have a roughly linear phase within the band of interest here, so it's like a straight line, and that is giving us just a simple phase shift. So we know now that a reconfigurable intelligent surface have elements that are small and that we can control the phase shifts. And this resembles once again how beamforming can be done in 5G. And there are 2 ways of implementing that. One of them is designed for non-line of sight scenarios where we have a complicated propagation environment with many different paths. And in these scenarios, there is no particular beam angle that we would like to transmit in that is good for all subcarriers, because these different objects are in particular directions, but they superimpose differently and give us some constructive or destructive fading behaviors depending on what frequency you're at. So here are the subcarrier indices, and bigger numbers in terms of path loss is better. To communicate over such a channel, you need digital beamforming, which means that you have multiple antennas that are each of them individually connected to a digital baseband where we can control exactly the signal that are being sent. So we can send signals in different directions on different subcarriers. If we are instead considering some simpler propagation environment, where there is one line of sight path in the 0-degree angle here that is dominating on all the subcarriers, while we have some fluctuations also due to non-line of sight paths. In such a scenario, sending a beam in that one direction on all subcarriers will not be optimal, but it will be quite good. And in these cases, we can get away with something known as analog beamforming, where you from the digital baseband only generate one signal, then you send that signal to each of your antennas, but you phase shift them differently on each of the antennas. And in this way, we can generate just one angular beam in one particular direction, but that is enough in a line of sight scenario. And this is also what a reconfigurable intelligent surface is capable of doing, taking incident signals and phase shift them in order to send them in one particular direction. And to drive home that point even more, let's look at a simulation scenario where we have a transmitter, we have a receiver, we have an RIS. There is a static path between transmitter and receiver, which is a non-line of sight path, so there's many different objects in different angular directions. There is a line of sight path between the receiver and the RIS, it's just 20 meters. This might be me standing in this virtual office that you saw before. And then we will be switching between having a link between transmitter and the RIS, which is either line of sight or non-line of sight. If we have a line of sight path, well then here is the data rates in megabits per second that we can deliver depending on how much spectrum we're having. One of this curve here is what we get if we have an upper bound for the case where we can be optimizing the RIS individually on each of the subcarriers in some kind of digital beamforming like approach. So that is the best that can ever do. Then we have the dashed curve, which is what we actually can achieve by taking the signals coming from a transmitter and reflect it in the line of sight direction towards the receiver. And it is very close, so there is not much we are losing from the extra paths around the line of sight. And then we have the dotted curve here, which is when the RIS is replaced with a metal plate that just happened to reflect the signal depending on how it is directed. And we can see that we definitely see a big gain in terms of having an RIS in this scenario. But if we remove the line of sight path between transmitter and RIS, all of the numbers are reducing, the upper bound becomes very close to the case with the metal sheet, and the optimized RIS is indistinguishable from the metal sheet because the signal comes from so many angles and need to leave in so many angles, so we can only pick one direction and reflect it a bit better than the other one. So that is meaning that an RIS is only effective to create this kind of virtual line of sight. So we need to deploy it where the transmitter and the receiver are seeing it, but they might not see each other. So with this in mind now, how can we optimize the RIS and how can we do channel estimation? So we can study this as just one frequency because we have this line of sight like path. Suppose the transmitter sends a signal to the RIS, there are n elements in the RIS, well then there is channel coefficients A1 to AN describing those channels. Each of the elements have a phase shift that it's generating. I have the theta here that is describing those phase shifts, and then from each element to the receiver there is a coefficient B1 to Bn for different elements describing the channel. If we now send a signal X, that signal will propagate through one of the channel here, say AN. It will be phase shift by theta n, and it will be multiplied with Bn here as well. So this is the impact of the nth element. We sum up the received signal through all of our capital N elements. We add some noise. They have some signal power, noise power, and that is our received signal. The RIS is now controlling how the coefficient in front of X is behaving. So our achievable data rate might be log 2 or 1 plus the transmit power divided with the noise power times G, which is this coefficient in front of X with an absolute value square. We have the A and B that are given by nature, our communication channel, and we have the theta that we can control. So if we are taking these vector notations, we take A and B and multiply them together in an element-wise way, so A1, B1, A2, B2, and so on, then we have an inner product or dot product with the phase shift vector. And we take the absolute value square of the result. And we can choose this vector now to make G as large as possible. How is that done? Well, we know that if we're adding up positive numbers, they are stacked on top of each other, while positive and negative numbers partially cancel out each other. So what we would like to do here is to make sure that all of the terms in this summation has the same phase. For example, they are positive. So therefore we can take each theta and we assign it to be the same as the argument of phase of A and Bn, and because of the minus sign here, that is cancelling out it, and we get only positive numbers to add up. So this is how you are configuring an RIS to achieve the maximum value. But the essential thing in order to do this is that we need to know something about the channels. Not the entire A and B vectors, but at least the phases of the so-called cascaded channel A times B. Let us now have a look at how the end-to-end channel G here becomes when we have configured the channel perfectly. For example, we can consider a line of sight case where we have isotropic antennas at the transmitter and the receiver, and each of our n elements here have an area A. There is a distance dt between transmitter and RIS, then each of the an factors will have an absolute value square, that is lambda square over 4 pi dt squared, and then multiply with the area of an element. So this is the free space propagation conditions. And for the channel between each RIS element and the receiver, we get the same kind of formula, we just replace the distance with the distance between them. Then the optimized channel gain, when we have configured RIS perfectly, will be that we are summing up these values in amplitude, we are then taking the absolute value square, and this will become this formula, where we can see a number of things, that the propagation distances are multiplied together, so this factor here can be rather small, while we also have the number of elements times the size of each one of them, so the total area, squared. And this is known as the squaring law, and because this factor here, which is essentially the path loss to and from an element multiplied with each other, can be very small. We typically need n to be at the order of hundreds in order to compensate for that. But because of this quadratic behavior here, we also pays off more and more to have large surfaces. Why do we get a signal to noise ratio that is proportional to the number of elements squared? Well, there are two things that are happening here. We are sending a signal from the base station towards the RIS, and then the larger the surface is, the more energy it will collect. So we collect energy proportional to the size of the surface. And then each of the element is phase shifting the signals, then it beamforms towards the receiver. And that is when we get the beamforming gain proportional to how many elements we're having. So we have n for the reception and n for the retransmission of the signal. How can we then estimate the channels? The problem is that the RIS is blind because it just reflects the signal, and then we can observe at the receiver if we get a good or bad signal quality. And in order to address this, some people have suggested that maybe some of the elements in our surface will actually have receive antennas. And that can be used to estimate path of the channel. The problem is that it will not really be a low-cost surface anymore if we build it in this particular way, because even if, say, 5% are these antennas, if we have 200 elements, we still need 10 antennas, so it starts to become large numbers and quite an advanced MIMO technology as soon as we turn some of the elements into actual antennas. So instead of approach 1, we want to take approach 2, which is the following. We have a user device that sends a known signal repeatedly. The RIS is switching between different configurations, so you can measure at the base station how strong the signal is, both in amplitude and phase. And then we estimate the cascaded channel, we compute what would be a preferred configuration, and then we feed it to the RIS that is then switching to that configuration during data transmission. And this is the path forward that we will now have a closer look at. We are now going to transmit multiple times different signals XL. They are going through our channel, and then we have a configuration theta L with an index L here that we will be changing over time. We receive YL and we have noise WL. Let's suppose we actually repeat exactly the same signal over and over again. Then we are changing the configurations, θ1 to θl, we put them in the matrix B. Well, now the received signal, y1 to yl, can be written in this matrix form here, using this B matrix as being the different configurations. And we have the noise vector over here. And the interesting thing then is that y is the vector that we observe, w is some unknown noise, and a times b, we will call it c from now on. This is the thing we would like to estimate. And b, our known configuration that we have picked in advance, so for that reason we know that thing. We can write this in matrix vector form like this. And the problem is to estimate c from y. Particularly we would like to do it by only sending a few number of pilots. We will first consider the classical maximum likelihood estimator, which is one of the classical methods in signal processing. Here is our received signal model, and if we suppose that we happen to know the c vector, then only the noise here, which is now assumed to be complex Gaussian with the variance sigma square, is unknown. So we can take y and subtract this factor here with the particular c, and we only get the noise. So we can write up the probability density function of y for a given c vector, and it has this particular form. The maximum likelihood estimator would like to find the value of c that makes this probability density as large as possible. And we are picking all possible c vectors of length n. This is the same as minimizing the term up here in the exponent. And if you solve this thing, well then this is the result here. We take y, we multiply with the pseudo-inverse of the B matrix, and then we divide with the transmit power. Even if you can do this with the pseudo-inverse, you want to have at least as many pilots being transmitted as you have elements. Otherwise you just get some weird estimate of your c vector. This tells us that we need many pilots. So if we have 100 elements, we need 100 pilots, and it just keeps increasing with the number of elements. We will call this the least squared estimator from now on, because we will design a more intelligent maximum likelihood estimator in order to reduce how many pilots that we actually need to send. Now we will utilize the fact that it is virtual line of sight paths that we want to generate. So we have a user that is in line of sight to the RIS. We have an unknown channel, but it's parameterized by the angle. And then the RIS and the base station are at fixed location, so the channel between those ones will not change very much. We can assume that that one is known. So if you take a received signal model again, it's only A that is unknown, not B. We rewrite it like this, with A times the diagonal matrix with the B entries, and we have the same thing, but we have exposed A on itself here. We know that A is a line of sight channel, so it will be given by an array response vector responding to what angle the signal is coming into the RS from. There will be some phase shift and there will be some channel gain as well, depending on how far away the user is. But this means that the channels that we would like to estimate must have this structure. So we're only interested in finding this alpha, the omega, and the angle, and find the most likely channel of this form. So we can design a maximum likelihood estimator for this kind of line of sight channels, where we are not searching for just any A vector, but only the A vectors in this calligraphic A set of line of sight channels. And in the same way, we are then minimizing the term in the exponent with respect to only the A vectors of the right kind. And in this recent paper, we provide you with the actual estimation framework. There is a way of computing the channel gain and the omega phase shift, and then in order to find the angle, we need to search through a number of different angles with a numerical search. You make a search grid, depending on how many elements you have, you need to have a finer or coarser grid, and you find an angle from that one. This is something that I just showed you for a case where you have only one angle, but you can make this much more complicated. So we can have multiple angles both in the azimuth plane and the elevation plane. We can have particular angle intervals where we can only have use in those directions due to geometry. For example, the uses might be underneath the RS. And we can also extend this to the radiative near field, where we can actually also see that this array response have a dependence on how far away you are as well. All of these things works and is covered in this paper. The main thing then is that if we would like to compute our achievable rate, well, we are configuring the RIS based on the estimate of the channel that we're computing. And then we get the rate here that will not be the maximum one, but it should still be close to the maximum one if we are successful with our pilot transmission. Let us now have a look at how this improved maximum likelihood estimator works. We consider a scenario with 1024 elements, and then we have particular parameters in terms of how strong the channel is, like minus 10 dB during the data transmission and 10 times larger during the pilot transmission, because we can spread out pilots over the frequency domain. In this paper, the goal is to be able to estimate the channel very well with very few pilots. And then it's important which RIS configurations we use during the pilot transmission, because we will not look in all possible directions. So we have an adaptive approach here where we are sending pilots with one configurations, and then we guess what the channel direction is to the user. And then we use that estimate to determine what configuration we will use at the RIS during the next pilot transmission. And there are two things that happens. Either we look in the direction where we think the user is, and we discover the user there and we get even better estimates, or we discover that there were no user there, we were just messing things up because we have not explored all dimensions yet. And whatever happens, we get more and more useful information. Here is then the spectral efficiency in bits per second per hertz that we can deliver depending on how many pilots we are sending. And note here that we use logarithmic scale because we are going from 2 pilots all the way up to 1024. At the top we have the capacity curve, so this is the best thing that we can achieve if we have perfect channel state information. Then we have our proposed method here, that after 2 pilots have quite a decent performance but is still far from the capacity. Then after just a few pilot transmissions, we start to get close to the capacity. And we have 4 pilots that are sufficient in order to get really close to the perfect channel state information case here. And this is because we have 2 angles to estimate, we have 1 depth, and we have 1 static path as well. So we are considering actually a bit more complicated channel in this paper than I have been describing earlier in this video. So after that, we have enough pilots to estimate all of these parameters, and then we are getting close to the capacity. If we are instead using this traditional least square method, we can apply it already with 2 pilots, but we have a huge gap and we need to go up to 1024, so the same number of pilots as we have elements before we get a performance that is really good. So that was one example of how array signal processing methods like this parameterized maximum likelihood estimator is really important in order to be able to operate RIS-aided communication systems with very few pilots and make it real-time reconfigurable. But there are some other things that also array signal processing can help us with. One thing is broad beamforming. So before we have reconfigured the surface in order to serve one particular user, we probably wanted to help the base station to broadcast its signals. And one way of doing that would be to take the signal that reaches it and spread it out in all angles isotropically. And if we try to find an RIS configuration that spreads out the signal in all angles, both azimuth and elevation, so that we should have a array factor or gain in different directions that is constant, you will figure out that that is impossible. You will always have fluctuation up and down. Some directions are stronger and some will have nulls that really goes down badly. So we can't do a broad beamforming with such an RIS without having nulls in it. But you can build an RIS with elements that every rows have opposite polarizations. So one of them reflects signals in one polarization, one in the other one. And then you can configure the horizontal polarization to reflect signals in some directions, vertical in some directions, and match so that the valleys in one of the spectrum is where we have peaks in the other way, and design them so that they add up. So signals, if you count both polarizations, are spread out equally in all angles. And that will then help us in order to give good coverage also of control signals being broadcasted by the base stations. And the tool to do this is to do a discrete Fourier transform on the received signals for different angles to compute our array factor, and then find phase shift that can make this combined array factor very flat. This is known as Golay sequences, and you find the details in our recent paper. Even if there are many good things that an RIS can do, there are also some issues when it comes to actually deploying them in practice, which we call the dark side of the RIS. And one thing we should remember is this phase response that I was showing you earlier. Within our desired band, we have a particular phase shift that we can design that is the thing we want to achieve. But outside that band, we will also have some other system operating. Maybe another telecom operator have paid a lot of money for the spectrum to use there. And we will change the channel also in those bands, even if the phase shift will be different. Because an RIS is not like a passband filter that takes just a signal at one frequency and changes phases. No, it takes all the signals in a quite large band and changes their phases. And this is problematic. In the best case, it might be that, well, the surfer will just create some extra small-scale fading variations because it's like objects are moving around every time we are changing the RIS configuration. But in the worst case, if you have two base stations close to each other, they have one RIS each, and you have a standard that tells you, well, at the same time, you should estimate a channel and then you should transmit and switch between uplink and downlink in the same way, which you typically need to do in 5G systems. There is a big risk that the two base stations will estimate their channels and they will get some leakage from each other's RIS, and then they will change the RIS configurations based on their estimates and mess with each other's channels. And this is creating a kind of pilot contamination where even if the base station sends signals that are in their own bands, they're changing the channels in a way that is destroying each other's channel estimates. And this might be one of the showstoppers that needs to be overcome before RIS can actually be utilized effectively in practice. Finally, erasing the processing is really important in order to make the RIS operations efficient in practice. We asked this question in a paper a few years ago: can we control an RIS in real time? And the answer is yes, if we are using geometric-based estimator from erasing the processing literature. And whenever we would like to generate this virtual line of sight path, which is the really important use case for RIS, we can do it. And we don't need data-driven methods for this. ML here stands for maximum likelihood, not machine learning. And what is then a convincing use case of RIS in practice? That was one of the other questions in our paper a few years ago. And this is still unclear. Telecom operators are exploring this. I think that this relaying kind of modes and things that can improve your channel rank might be the most important use cases. But 3GPP is currently studying what they call smart repeaters, which is a different name for both RIS and other kinds of repeater technologies that might be utilized in 5G and 6G. If you want to learn more about this, I recommend you to read Chapter 9 of our recent book here, Introduction to Multiple Antenna Communications and Reconfigurable Surfaces, which is open access and you can download it from nowpublishers.com. And it will explain most of the things in this video all the way from the first principles. Thank you very much for watching.